On 11, we're talking about silver chromate and water. So it's going to dissolve like this, right? You're going to get 2 silvers and 1 chromate ion. And if we are told that the molarity of the silver is this, then the chromate must be half of that value. So here's the molarity of the silver. Here's the molarity of the chromate at half that. And therefore, the KSP is this squared times this to the first power. In 12, we put some of this solid and some of this solid in different beakers, and we give them a stir and let them settle out, and they make a saturated solution of each in their own beaker. Now, the fact that it's 50 milliliters of pure water ends up being immaterial because we are asked for the concentration, and the concentration it will set up will be the same no matter how much water you use, assuming that you have at least enough solid. I mean, you can't put a 1 grain in a swimming pool and get a saturated solution, but we're going to assume that they put in enough because it says it was a saturated solution, and a saturated solution is characterized by a few things. It has a maximum molarity of the ions, and it's the point where K is true. It's the point where the equilibrium is true. So we're asking for the concentration. So the 50 milliliters is immaterial. Let's disregard it. So what can we find out about these things? Well, we know that this is the formula. So when it dissolves, the solid is going to make these ions. Therefore, you get one of this and one of that. And the value of each of these will be K. When I square root the KSP, I get X, and X is the value of the Ag plus molarity. When I do this one, I get 2 Ags and 1 carbonate. So I end up with my classic 4x cubed. Divide by 4, cube root, and I get X. But remember, the molarity of the silver is 2X, isn't it? So it's double this number times 2 will get you this. And B has more silver even before you double it. So the one that has the greater silver is the silver carbonate. In 13, I have a fake KSP of lead to iodide, and I just made that because it makes it so that we can do this math without a calculator, which they really think you can do. We do need to learn to do some decimal manipulations and so forth, and even square rooting of this kind in our heads. So this is good practice for that. So we have a molarity of lead nitrate, and I know that there's only 1 lead coming out of every lead nitrate. So this molarity is also the molarity of the lead ion, because one of these will get you one of those. The nitrate is immaterial as a supersoluble. The potassium here is immaterial as a supersoluble because neither of those will ever try to make a solid in water in our problems. So we can just disregard them mathematically. So we have this molarity of lead, and we're going to add potassium iodide. So all the iodides come off and become iodide ions immediately. So when would this stuff start to form? Well, it would start to form when KSP is true. And if that's true, then what we've got is our dissociation reaction running backward. So this would be the solid, and these would be the aqueous. And if KSP is true, then it would be when this to the first power times this value to the second power multiplies out so that K is true. And after that, you can't violate it. And if you add just the tiniest bit more, you will get a precipitate. So what is the lead ion concentration? And it's that, because one of these will get you one of those. So I'm going to put that in here. This value is X, and it's really tempting to say, no, it's 2X, but it's not, because this iodide ion did not come from the dissolving of this solid. It's from the dissolving of this solid, which happens basically immediately. And this value is just simply this value, whatever it is. We do need to square it though, because the value would be squared because of this too. So we're going to put in this value for the lead. This stands for the iodide. We're going to divide, and that means move the decimal up 2 spots. When you divide by a small number, the answer gets bigger. And then we're going to square root. Obviously, the square root of 9 is 3. And here's the part that seems to get skipped in math classes. 10 to the minus 6 square root is 10 to the minus 3, because what times itself will get you 10 to the minus 6? And the answer is 10 to the minus 3 times 10 to the minus 3 will get you 10 to the minus 6, because when we multiply these, we add the exponents. So essentially, you sort of take half. And I know that's not literally true, because I know that this is bigger and this can't be half of that. You take half the absolute value, maybe we should say, and then keep the sign. On 14, we're looking for something that won't affect the solubility of this. So here's the dissociation reaction, solid, aqueous, aqueous. And we're looking for something that won't affect these. Now, obviously, if you add something with iron 2 in it, it will affect the solubility. It would drive it down because by Le Chatelier's principle, if you add something on the right side, it will always drive it left. Or so if we add something that has carbonate, that will drive it left. Now, the other thing that's much more open-ended is there's just about 1,001 things that could either grab the iron or grab the carbonate and remove them a bit from solution, which would drive the whole reaction to the right. Well, one of the things that you could name is KCl because, of course, K is a supersoluble ion and just has no chance of grabbing the carbonate. And Cl turns out not to be an exception to the solubility of iron 2. So it wouldn't grab that either. And of course, there's the other stuff that you could name, which are all made of all supersolubles, which would never affect anything like you could say potassium nitrate, anything with those, potassium perchlorate and everything, you could keep on going. Ammonium perchlorate and lithium nitrate and so forth. If you could combine supersolubles, obviously those would not affect the solubility of the solid either. On 15, we see that we have NaCl, which is a classic supersoluble with the sodium in there. We probably know table salt just dissolves and dissolves, and in these kinds of proportions, it dissolves just very well. So we're going to count all of this as coming apart. And again, sodium doesn't factor into K math, so we're going to say that for all practical purposes, that disappears. And let's just assign this to the Cl minus molarity. And then we have some moles of this. Now, this is not supersoluble, and it's going to come apart, but only to some extent. And if it does, this is what we get. Of course, we lose some of this, we get some of this, we gain some of that, but this is the solid, so it also doesn't affect any K math. So what's the value? Well, they mean in a saturated solution. So let's mentally do that. In a saturated solution, KSP is true, which I was given KSP here. So if KSP is true, the silver ion will be, well, just whatever managed to come off this, and the chloride ion will be whatever came off the silver chloride plus the 0.01 molarity that came from the table salt here. Now, they're both to the first power, so we don't have to worry about that, but this will be X and this will be 0.01 plus X. But with a K way down there, KSP, that is a very small KSP. Let's just go ahead and assume that this is so small that compared to 0.01, it's mathematically inconsequential, and I'm just going to cross it out. In that case, we can just divide, and we have X, and X is the value of the silver ion, which is what we were asked for up here. 16 attempts to catch kids in a misconception here. The molar solubility of a solid can change, and this is what we've been talking about, say up here. So if we dose this with Cl minus to begin with, then the molar solubility of the silver chloride went down because this will stop dissolving when K is reached, when the value of K is reached, whatever it is. And in this case, it's pretty small, but whatever it is. So if you pre-dose this solution with Cl minus, it's easier to hit K because this times this equals K is the point when this will stop dissolving, but this number is already sort of artificially large. So if you pre-dose the solution with ions on the right, the molar solubility will go down. The presence of dissolved ions on the right side will make the solid less soluble. Conversely, if you already had some of this in there, and you started pulling it out by some means or precipitating it with yet another reaction, then this would go down and it would be harder to get these values multiplied together to reach K, in which case you have to do more dissolving than you used to before. So removing the ions will make the solid more soluble. What never changes at the same temperature is KSP. On 17, we're dealing with a solid of silver carbonate, and it just says on A, right, that's the dissociation equation. So we get two of these and one of those, and so there's our dissociation equation. Now, a certain mass, maybe that'll come up later, it won't come up here, is placed in pure water to form a 1 liter solution. But the point is, undissolved solid remains at the bottom. So we have a saturated solution, don't we? If we dissolved as much as we can, and we know that they can't fit any more in because there's still solid remaining. So we've dissolved as many ions as we can get. So when you dissolve this stuff, you get two of these and one of those. So this is, if we dissolve S of this, we get S and 2S. And of course, don't forget to take this value then to the second power because of this. So this is double the quantity of that. And in the K-math, this is also squared because the 2s is squared because of that too also. So we get our classic 4s cubed. And so we're going to divide by 4, cube root, we get the value of s. But remember that the question was the concentration of Ag. And Ag is 2s, so it's double that amount. On double I want the liters that will dissolve the amount of solid that we were given. We were given this many grams of silver carbonate, and they gave me the molar mass just to speed this along. So what I need is the molarity that this can achieve. This is the molarity that it can achieve. So in case this didn't get through before, S is the molar solubility. It is the maximum number of moles of the solid that can dissolve. It's not the maximum molarity of these ions because they're going to be different because you get 2 of these and 1 of those. It's the maximum molarity of this, or the maximum number of moles per liter that this can achieve through dissolving at this temperature. This is the maximum molarity of the salt as a whole that it can achieve. So we can find the moles of 0.05 grams, divided by the molar mass gives us moles. And if we can multiply by the flipped molarity, the moles, remember this is going to cancel out, give me moles. That achieves moles. And the moles times the flipped molarity will cancel out moles and give me liters. Another way to view this would be to put the moles over the liters, and the bottom of the bottom is the top of the top. If you don't know what I'm talking about, you might put that phrase into the internet and find out, and we get the same math. When you take this value, which I didn't actually do, and put it in here for moles, you get the same math, don't you? I use the longer decimal. You divide by the moles part, and you get the number of liters that it would take to achieve that molarity using that number of moles. On C, we're asked for the molar solubility. Now that's S. Now it may seem we know S, but we're pre-dosing it with this solution here. And of course the nitrate is super soluble and won't figure into any K math, so let's disregard it. But one of these salt particles will give me 1 Ag. So this is the molarity of the Ag before I even get started. So while the solid will dissolve like this and give me 2 Ags and 1 carbonate, the molarity of the Ag is already pre-dosed, so it's 0.1 plus the 2s that would have come off the solid, and sort of over here if you visualize the solid being written over here, and the carbonate would be S. Now this sets up a quadratic formula, which the test is not going to do, and plus honestly it doesn't matter, because with a KSP in the E-12 range, the amount that 2s is compared to 0.1 is just simply immaterial. Let's just cross it out and ignore it. Then all we have to do is divide, and we have S, and S is the new molar solubility when we've predosed it with this molarity of silver ion. 14 is a style that they don't seem to do anymore on the test, because what you're supposed to do is take this reaction and note the K, all right, and then find the K of this. Well, the trick here is that they don't say this, is you're supposed to take this reaction, combine it with the K and the reaction from part A and the initial instructions, and combine them into this overall reaction here. This one is that one. So here's the reaction from the top and the K, and here's the reaction they just handed us and the K. So these two together can make that if you massage it correctly. So let's check this. The Ag 2CO3 is on the left, and it is not multiplied by anything, so let's just leave this one as is. Therefore the K remains. I don't know really what good that does us, and honestly that doesn't do us any good either. I'm just going to ignore that. Of course it's true, but it doesn't really help us find K of the overall. What I need to do is multiply the K's given in the correct changed way if necessary. If this needs to flip, then I multiply this one by the inverse of that one. And in fact, in this one, I see that I need to multiply this by 2. Now, that's not quite so obvious. When I go looking for the Ag plus, I say Ag plus has an exponent, the coefficient of 1, and it's on the left, and in fact, it's gone. It's gone because this one canceled out that one, but only if we multiply by 2. Well, that may not be super obvious, and if you can't figure that out, you keep on going and go to, say, the next chemical. It's 2 ammonias on the left, except here it's 4 ammonias on the left. Well, there we see we multiplied this one by 2, which means we must have multiplied the whole line by 2. So this one is multiplied by 2. When you multiply everything by 2, then the coefficient of all the chemicals becomes double what it used to be, and therefore you get the squared amount of the previous K. So we're going to take this times the squared amount of this one, which is what they wrote here. Again, this is kind of immaterial. What we're going to do is take the first K times the second K squared and get the new K of the overall reaction, this one or that one, same thing. So does the addition of ammonia increase, decrease, or have no effect on the solubility? And it took me a while to see what they're talking about, but what we mean is this overall reaction is our solid from the top dissolving except in the presence of ammonia. So we just found the K for that, didn't we? We found the K is 2.1 E negative or E positive 3, when previously it was in the E negative 12 range, which is really small. And this is kind of surprisingly big, whereas the other is remarkably small. So the addition of ammonia makes the solubility go up by roughly just under a quadrillion, which I would say is a substantial increase of the solubility.